The thing that I also notice is that a lot of people lose points by not double checking their answer. When you double check your answer, how do you double check? Because you don't know what the right answer is. A lot of people, when they double check, they just look in the solutions guide or they look in the back of the book for the answer, right? And they get in the habit of that. But when you don't have the answer and you can't look it up, how can you double check? Well, a lot of people just leave it at that because they can't find the answer anyway. But there's certain things you can do to double check your answer. Can you give me an example of one thing you might be able to do to double check an answer? Well, one example is just, does it make physical sense? Does the magnitude seem reasonable? With scientific notation and worrying about sig figs and this kind of stuff, a lot of people lose sight of the numbers. And so in some calculations, maybe not so much in Chem 1A, but in Chem 1B, sometimes I'll get temperatures that are like 3 billion degrees C. 3 billion degrees C, is that something that's easy to achieve? But it doesn't seem like all that. It seems pretty benign because it's just 3 times 10 to the 9. 3 times 10 to the 9, we're used to dealing with 10 to the 23 and all these huge numbers, but you got to put things into perspective. You're going to have huge numbers for some things and extremely small numbers for other things. And so, for example, 10 to the minus 18 calories, is that very many calories? 10 to the minus 18 calories? No, it doesn't seem like that many calories. It's a minuscule amount of calories. But for a single atom, this is a tremendous amount of calories. So we put things into perspective because we know, what the numbers mean. Does somebody, 3 to 10 to the minus 18 calories doesn't seem like much energy at all. To others, that's a significant amount of energy. And so it depends on what type of problem you're doing in the context. And so we can put things into perspective because if you're getting 10 to the minus 18, let's say you have a cup of coffee and you need to heat it up, is 10 to the minus 18 calories going to do much as far as heating up a cup of coffee? It's going to do nothing. I mean, it's like noise. You aren't going to notice any change in the temperature, right? A cup of coffee. In fact, you wouldn't be able to measure a change in temperature there. And so we work with 10 to the minus 18, not calories, but what's the other unit? The SI unit. Calories is not the SI unit. What's the SI unit for energy? Joules. And so we're going to look at 10 to the minus 18 joules. It's nothing for a cup of coffee. 10 to the minus 18 joules is huge for a hydrogen atom. You subject a hydrogen atom to that much energy and it's going to knock the electron out to infinity. Okay? Or, what infinity just means it's completely ionized. Well, anyway, let's think about the numbers and see, do they make physical sense? And the other way to double check your answer is to do what? Make sure the dimensions work out and re-punch the numbers into your calculator. Sometimes you make the same mistake twice, punching it in your calculator. But I noticed that, some of the calculation errors I see are just simple miskeyed, and so the second time you key it in, it's less likely, third time, unless you're automatically doing this, subconsciously. And just hitting the wrong key each time. But just double checking it on your calculator, can save you points there too. And so, anyway. Let's continue on with some of these problems here. Any problems with signing up for Piazza? No, it's pretty straightforward. You say? Okay. All right. Take a look at that problem. What was the number of that problem we were working on? 71. Oops. so let's go back to 71. We're going to just look at maybe finish up 71 and then take a glance at some of the other problems and then move on to chapter 2 today. So, one thing, like I said, that's different between Chem 4 and Chem 1A.
79.
Oh, 79, okay. Okay, let's take a look. All right, 79 is filled with ethanol. Actually, we need to finish 78. So I guess I didn't do that correctly. So, the density of methanol we can calculate. Let's go ahead and do that. The density of methanol. Now, methanol, I'm going to use this abbreviation, MEOH. It's a common abbreviation for methanol. That way I don't have to write it all out. But this just stands for the density of methanol. Can you guys see this okay? The screen? Maybe I'll switch to blue here. The density of methanol is equal to the mass of methanol, right? MEOH, divided by the volume of methanol. And so we just need the mass of methanol. The mass of methanol we can get from here. We got to do this, 33.490 grams. Right? And when we do this, a subtraction, I like to put it so that we can align the decimal places. Minus 25.601 grams. And so this would be the methanol plus the picnometer. This is just the picnometer. And then we get the mass of the methanol. Okay, and what does that come out to? Well, 10, it's going to be 9, it's going to go 8, 14, 8, 12 would be 7. 7.889 grams of methanol. All right, so we have 3 decimal places. This gives us 4 sig figs. Even though this is 5 sig figs, we only end up with 4 sig figs because it's addition, subtraction. We don't care about the sig figs. What was the volume of the picnometer that we calculated yesterday? Did we calculate the volume of the picnometer? Yeah, can somebody remind me what the volume is? What? Somebody write it down. 9.96884. Okay, and how many sig figs were we allowed? 4. And so what I'm going to do is I'm going to write the 4 allowed digits like this, and then the extra digits like this, so we can kind of keep track of them. This is this was in milliliters, right? Okay, and so that entire volume should be taken up by the methanol. And so can somebody calculate the density of the methanol? Four. More digits, please.
Okay, fine, just 136.
Okay, let me just, Stanley, I want you to break that habit, because I want everybody to not round. It's easy to round it in your head, right? You just look at it on the calculator, you just round it. But I want you to get in the habit of doing this. Get in the habit of writing down extra digits and showing me the rounding step. If you don't show me the rounding step, I have to deduct a rounding. It's a very small penalty, but I'm going to deduct if you don't show me the rounding step. And so 7, 9, rather than 1, 4, it's 1, 3, 6, 5, 8. All right, here we're only allowed 4. The units are going to be grams per milliliter. And so we'll go ahead and now round it, 7914 grams per milliliter. Okay, I want you to show me that. A couple of reasons. One is sometimes we need this number for a subsequent calculation. If we need this number for a subsequent calculation, sometimes we'll carry extra digits to minimize the error in the subsequent calculation, to maximize the accuracy. All right. And in fact, we do need this number for a subsequent calculation. We need it for number 79. And so I want the, and so going to number 79, it's the same thing, except we're going to calculate the density of ethanol. And so the mass, this is going to be the density of ethanol. Ethanol, I go capital E, lowercase t, capital OH, ETOH. Ethanol. The density of ethanol is equal to the mass of the ethanol. And so the mass of the ethanol is going to be the total mass. So the total mass is 33.470. 33.470 grams of ethanol plus PIC minus the mass of the picometer, which was 25,601. 25,601 grams of picometer. This is going to give me 9,687 grams of ethanol. So, is that right? Yes? No? That's right? Okay. Divided by the volume, we have the volume. Volume is going to be 9.96884 grams, or not grams, milliliters. Okay, so this part is the density here. And this is going to equal
0.789359.
okay, 0.789359 grams. Okay, which one's more dense? This one's more dense. Right? The density of methanol. That's kind of weird because methanol is CH3OH. Ethanol is a bigger molecule, it's CH3CH2OH, right? And so why wouldn't ethanol be more dense? It's a bigger, heavier molecule. Why isn't it more dense? Well, what we do is we double check the calculations. The calculations look okay? Calculations look okay? But if the calculations check out okay, could there be an explanation of why methanol might be more dense than ethanol? Ethanol has a lower mass, or bigger. Ethanol has a higher mass, yeah.
It's because the hydrogen bond is bonding with the oxygen.
Hydrogen bonding?
Yeah.
That could be. Hydrogen bonding. The methanols are going to be better at hydrogen bonding than ethanols. Why? The methanols are going to have stronger hydrogen bonding interactions than ethanol. Why? Per molecule. Makes sense. Well, actually, we'll review a little bit. You know, these are called hydrocarbon groups here. The hydrocarbon groups, are they very polar? Hydrocarbons, if you think of hydrocarbon, think of something that's consists of hydrogen and carbon. Can you think of the compound or class of compounds that consist of hydrogen and carbon? Maybe you haven't covered this in intro. We're going to cover this in Chem 1A, Chapter 3. We're going to look at the hydrocarbons. Hydrocarbons are like oil. Oil are nonpolar. Whereas this part, the OH part is quite polar. And in fact, OH is so polar, hydrogen bonds. And so this has a larger hydrocarbon group. In fact, when the alcohols get very big, the hydrocarbon part dominates. And so big alcohols are like oil. You know, you can't mix them with water. Did you know that? When you get to like butanol, pentanol, butanol is 4 carbons. Pentanol, do you know how many carbons it has? You can guess 5 carbons. Hexanol, 6 carbons. When When you get to hexanol, it doesn't dissolve in water. You know, these smaller, like methanol and ethanol, are what we call miscible in water. Miscible means it dissolves in any proportion. It's fully soluble in water. And so the small, what we call the small chain alcohols are highly soluble in water. The large chain alcohols aren't. But anyway, that could be one of the reasons. Yeah, better hydrogen bonding interaction maybe pulls the molecules closer together. Might be. Another thing we have to think about is how well they pack together in the liquid phase. You know, if they can pack together so that there's less empty space between the molecules, more tightly packed. It's like packing styrofoam balls. You pack styrofoam balls, you can pack them quite densely in a box, right? But if you have some floppy molecule like this, which is more elongated, and you try to pack it into a box, you're going to get more gaps, right, between the molecules, and they don't pack as densely, perhaps. And so, even though, you know, we might have thought that ethanol, this could be reasonable as well. Or we could check it out, we could check our answers. You know, the nice thing to do is to check our answers in the back of the book or wherever, right? But if you don't have that option, then you have to go back and think, do these numbers make sense? You know, do you ever go back and think about your answers? You know, does that answer make sense? Do you think you got that answer right? Because there's nobody to ask, you know, on a test. You can't come up to me and say, well, although a lot of people try, you know, am I doing this right? I can't answer that, right? And so you got to figure it out, you know, and then you go through this and make some kind of rationalizations, and then it seems to make sense, and then we're just going to go for it. Okay, but you would double check the calculations. The calculations look okay? Well, one thing we could easily see is that the total mass, here, the total mass with methanol is 33.490. The total mass with ethanol is 33.470. Did we pack as many atoms into the picnometer? No, so obviously ethanol should be less dense than methanol. And so that's a quick double check. And so these are things you do when you don't have the answer key, right? Or you should try to do. Also, we expect the density should be less than the density of water. You know, if you've ever had ethanol, and well, maybe, have you guys used ethanol in any labs? Well, you'll use it this semester. When you use ethanol, you'll notice it is less dense, more volatile than water. Okay. All right, anyway, let's continue on. So do you see these two are different densities? If these two are different densities, this gives us an option to do something. Well, actually, let's round this to the correct number of sig figs. What is this rounded to the correct number of sig figs? 9.4. For the final answer, I don't care. You could leave it like this. You know, when I see an answer like this, I take this as 4 sig figs. Or you could leave it like this, rounded. Either way. Sorry. All right, now, what are we doing in this next problem? In the next problem is this. I'm going to modify number 79 to make it easier. Because number 79 is tricky if you've never done one of these before. And so the way I'm going to modify it is like this. Did somebody write the numbers down? I just erased it. Shouldn't have erased that one. I wanted to keep that upper one. Number 79, this is a modified version, just slightly simplified to make it more straightforward. All right, we're going to have a mixture, methanol and ethanol. Do you think they'll mix together, these two alcohols? Yeah. Yeah, methanol and ethanol are miscible in each other. You can mix them in any ratio you want. They dissolve in each other quite easily. All right, so we have a mixture of methanol and ethanol. The density is going to be of the mixture. It's a homogeneous mixture. It's going to be 0.7905 grams per milliliter. And so the question is, what is the percent methanol and what is the percent ethanol in the mixture?
Sorry, where did you get that number?
I just made it up.
Oh,
I made it up. This is the modified. This is a number. This is what I mean by modified. I'm going to have a specific target. You get two types of questions as you continue in science, but you've only been exposed to one type of question. The one type of question you guys have been exposed to is solve for the answer, right? You don't have you probably don't have much experience with open-ended questions like this, This question is not solving for a specific answer. This is why I modified it, because this is much more what you're accustomed to. This type of question you get asked all the time because, if you're, let's say, as you progress in science, and I assume looking at this, everybody's science engineering major, but as you progress in science, people are going to stop asking you, okay, for this temperature, for this volume, for this, what is the answer, right? They're just going to ask you in general, what's the pressure of this, or what's this, or what's that, but they aren't going to give you specific variables to plug into some equation to calculate a single answer. What they want you to do is they want you to answer it like this. At high levels, we expect something like this, and at these numbers, we expect something like this, the general picture. And so the general picture would be something like this. Tell me about mixtures of methanol and ethanol in terms of density. What happens with the density? And then that would be a typical question, right? But would you be able to, once you have some practice, once you're thinking in that way, then you can answer those types of questions. But rather than a question like this, a mixture has this density. What's the percent ethanol and percent methanol? Right? Versus, tell me what happens to the percent methanol and percent ethanol as the density changes. So let me show you two ways of solving this. The two ways, everybody solves it using a system of equations. You use a system of equations, you got x and y. Let's say you solve for x and then substitute. You've all done that in algebra, right? But that algebraic system of equations is good for just solving for one answer, but you don't get the whole picture. The whole picture is the range. And so the way I like to do the analogy is, this is my, I don't know if I'd use this in Chem 1B, but I have the forest analogy. In chemistry, in intro chem and general chem, we're so focused on one tree in the forest. We want to, calculate that answer. But we don't know the extent or the range of the forest. We don't know where it starts and where it ends, right? We don't know the whole range and how it changes. Either as elevation changes or temperature changes or whatever else changes. And so the first way I'm going to show you is actually, maybe I'll have you do this yourself. Just a system of equations, you get one answer. And so you only know that one tree in the forest. The second way I'm going to show you is a graphical method where you kind of get the whole range. And so you can see how it varies. In order to solve problem number 79, you need to see the whole range. You can't just look at one value and answer it. Sometimes this is too hard. And so if you're given a question like that, what's often done in science is, okay, let's pick a value. If we pick a value, this is what you get, right? And so if a professor asks you something and you go, oh, not enough information, you don't write not enough information on the test, because that's not an acceptable answer. You have to come up with some kind of answer. And if you can't figure out the whole forest answer, then you pick a specific tree. And you say, okay, let's assume that we have this much. And then this is how you would solve it, right? So often when I give a question like that, and I have in the past where I omit a piece of information, see how people solve it, a lot of people will say, can't solve. and turn it in like that. Impossible. You can use this chair if you want. There's space over there. So, well, let's read number 79 and see what you think. What is the density? Okay. Of ethanol. We would have calculated it. How precisely could you determine the composition of an ethanol and methanol mixture by measuring its density with a pictometer? How precisely can you do that? How precisely? Okay, so they give you a hint here. Assume that the density of the solution is a linear function of the volume percent composition. So they're already telling you to look at it graphically. But anyway, here, how precisely could you do that? A lot of people will get stuck. If you get stuck, then just say, okay, let's pick a number and see what happens. You know, see how precisely you can determine it. And so this is what I did here. I'm going to pick this number and see how precisely we could do it. When somebody says precisely, what the heck are they talking about? Precisely. They're talking about what? Precision. Precision is related to what? Precision is related to what? Not accuracy. Precision and accuracy are not... Usually if you have high precision, you expect high accuracy, but not always. You could have extremely high precision and be terribly off because of miscalibration. Precision is related to what? Two things. Visually, what do you see in precision? The measurements. That's a good start. The measurements are really close. Good. The measurements are really close to each other. That's one. What's another way? I did these. What's another way you know it's high precision? Measurements are really close. The darts. What's another way? Sig figs. More sig figs, more precise. Right? Sig fig. Anything else? You know, those two things should have come up automatically, you know? Think about this. The people who reviewed yesterday or have been reviewing are going to be a step ahead. These are the pre-meds. The pre-meds are like this. The pre-med, I'll tell you, at UCSB, when I was a teaching assistant there, the class is 300 people. They surveyed the class. Out of the 300 people, do you know how many were pre-med that wanted to go to medical school at UCSB? Out of that class of 300 people, I'd say a good 80 to 90% of the people were pre-meds. Their goal was to get into medical school. You know, and they are very serious. I mean, these are people who, you know, who had this goal probably since, I don't know, middle school or 9th grade or something. We're working towards this. And they're going to do whatever it takes to get into medical school. But how many of those people are going to get into medical school? A small fraction of them. And so they were always looking. This is why, you know, pre-meds, you know, it's great. Pre-meds are, you know, great. A lot of my friends are pre-meds, but a lot of people, you know, in other majors don't like pre-meds because they're too hyper-competitive. You know, because they have to stand out above everybody else in order to get accepted into medical school. And so it's definitely changes. And so this is why I said, you know, it shocked me that somebody was doing all the homework problems. I would have never thought to do that. And I wouldn't have never done it until I saw, you know, all my pre-med friends were doing it. You know, why? Because they wanted to have that edge. They wanted to be number one. But anyway, so, you know, when are you going to get that? Well, the precision thing, you know, just repetition. But sometimes, you know, in this class, I'm not going to repeat myself that much. And so you got to repeat it. And the way you repeat it is this. I told you I'd take a complete set of notes, right? And then after I take the notes, I clear up any confusing parts by reading the book. If reading the book doesn't help, I look for another book. If looking for another book doesn't help, then I go to the office hour and ask. And then once it's cleared up, once I understand that concept fully, then this is the way I reviewed, because I told you my memory's bad. And so the way I had to review was every day I read my notes from day one through the current day, every day. And that way, by the time the test came, do you know how many times I heard precision? Well, every day for 10 weeks. If it was discussed on the first day, then I read it. And that's just to drill it down. There's some people, I was watching this thing about memory, at Stanford Medical School. They had one of the professors there. And the chair of the medical school, or the dean of the medical school, I forgot. It's on YouTube. He comes up there and he says, "Oh, I remember my days from organic chemistry where I remembered every single page of the organic chemistry textbook." He had like a photographic memory. But he said his memory's deteriorating with age. But then I thought, wow, that must be nice to have that kind of memory, which I didn't have, And so this is why I did it. Every day I would read and that's easy. Compare that to reading the book. You can't read the book. You can read your notes because it's not that much. And the notes is the most important thing. And so what I figured is by doing the notes and understanding everything in the notes, that pretty much guaranteed me a 90% on the test, because 90% of the test was going to be like that, and maybe 10% was going to be ultra challenging. So anyway, precision, this should be automatic. By the time the test comes, however you do it, if you cram it, the day before, you should know it. Well, anyway, have you thought about this question? Is this an easy question to answer? Does somebody have an answer for this? How precisely could you determine the composition of ethanol-methanol mixture by measuring its density with a picnometer? Okay, can we? So, can we determine the percent composition just by looking at the density here? And the answer is yes. Yes, we can. Because the density changes. We looked at the density of ethanol. And the density of ethanol, can somebody remind me of that? What was the density of ethanol again? 0.7, 8. Okay, give me more digits. 9.3, 5.9. The reason I'm carrying extra digits is because we want to see something. Okay, the density of methanol is equal to what? 7, 9, 1, 3, 6, 8 grams per milliliter. All right, officially we aren't allowed this many digits. I just carried it, and so really officially we're only allowed 7.894 grams per milliliter because of the uncertainty in this digit here. And this is 0.7914 grams per milliliter. And if we look at this, there's a difference here. If this mixture were just 100% ethanol, what would its density be? 100% ethanol just means pure ethanol. Its density would be 0.7894, right? If this mixture were pure methanol, what would its density be? Its density would be 0.7914. It would be more dense. And so if we had a 50-50 mixture, half ethanol, half methanol, do you know where its density would lie? If we had a 50-50 mixture, its density would be dead center in the middle. The more ethanol we have, the lower the density gets. The more methanol we have, the higher the density gets. And so to answer this question, the graphical method is the best. And like I said, they gave us a hint that it's going to be a graphical method of solving this rather than a system of equations. So let's go ahead and solve this. This is the way I solve this using the graphical method. The graphical method is like this. Which one is more dense? The methanol. And since the methanol is more dense, I like a positive slope here. And so what I'm going to do is I'm going to put 100% methanol here. If I have 100% methanol, I'm going to get the highest density, which is 0.7914 grams per milliliter here. If I have 0% methanol, then that must mean it's 100% ethanol. If it's 100% ethanol, what's its density? Its density is going to be down here at 0.7894 grams per milliliter. And so if it's 100% methanol, we have 0% ethanol. And so this is the graphical method. We have two unknowns. We'll call methanol X, we'll call ethanol Y. We have two unknowns. And so I told you that there's not just system of equations, there's a graphical method. This is the graphical method here. The graphical method is like this. Do you see the trend? This is our data. We're looking for pattern. Do you see the trend? You could use this chair. Erase out mine. It should go through both points. All right. We're going to assume this is linear. Actually, they say assume it's a linear function, right? So we're assuming it's a linear function. Is that a fair assumption? Yeah, I would think it's a fair assumption because, you know, what happens is as you increase the amount of methanol linearly, then the density should go up linearly. It shouldn't skyrocket up or skyrocket down in a nonlinear fashion. You know what I mean? And so this should be a linear function here. There are functions that are nonlinear too, so you know, so far we've only been dealing with linear, and but this is another example. In Chem 1A, I think all our multi-unknown problems are going to be linear functions. Okay. All right, now what do? We have the pattern, we see the trend. What do? We can calculate the slope, right? The slope is, we can get that our delta, let's go ahead and get our delta y. Delta y is going to be 0.7914 grams per milliliter minus 0.7894 grams per milliliter. This is going to give us what? That gives us 0.0020 grams per milliliter. That's our delta y, and our delta x is going to be, well, let's see, this is 100% minus 0%. This is going to give us 100%. This is percent methanol. Remember, we have to specify, you know, because it could have been percent ethanol. Why did I choose methanol? Somebody remind me why I chose methanol for my X and rather than ethanol for my X. It has a higher density, and I want a positive slope. If I chose ethanol, then I would just have a negative slope. It's not a big deal, but for me, I just, you know, if I have a choice, I'll just go positive. And so the slope is going to equal delta y over delta x, 0.0020 grams per milliliter divided by 100% methanol. And that gives me Actually, what does that give me? This would be 10 to the square, 10 to the minus 2, so 0.000020 grams per milliliter. What do? I can invert and multiply it. Percent methanol. Okay, so that's our slope.
When you plug into your calculator, are you plugging 100% or just 100?
100. Not 100%. The units are important. We got to retain the units because of the equation. What's the equation of the line? You could see this. The equation of the line is what? Y equals mx plus b. So let's just do it. Y is equal to mx plus b. Y is what? I didn't label the axis, did I? Density of what? The mixture. The density of the mix. X is percent methanol. And so what we have is we have the density of the mix is equal to the slope times X. X is the percent methanol plus B, the intercept. And so let's go ahead and do this. The slope, point quadruple 0, 20 grams per milliliter per percent methanol. Slope times X, which is the percent methanol, plus B, which is the intercept, 0.7894 grams per milliliter. Do the units work out? You know, you asked me that's a very important question. You convert from percent to decimal, right? We often do that. But in this case, you would have easily saw that it's wrong. It would have been wrong to convert this percent to a decimal because then these two units aren't going to cancel each other out, right? All right, what do you see that's a potential precision problem here? Do you see any precision issues yet? So far in this relationship? Yeah, what is it?
The amount of decimals in the slope versus
Yeah. Yeah, where we're going to have a precision issue is this. We only have how many sig figs here? Two. There are only 2 sig figs here. Which means that the precision of this method is going to be limited to 2 sig figs. Right? And the reason is because these two densities are kind of close to each other. The only way we could increase the precision is by doing what? The only way we could have increased the precision is by taking more precise measurements of the density. So for example, if we had 5 sig figs in the density, then we would have gotten 3 sig figs here. If we had 6 sig figs in the density, then we would have gotten 4 sig figs here. 4 sig figs, that's pretty good precision, right? But we aren't allowed these because the pycnometer isn't precise enough. And so what we need is we need something even more precise than that, or a different design of pycnometer, so that we could have measured this out to greater precision. Does that make sense? People who round off run the risk of sometimes when you know, if you get overzealous and round this off, then this is 0.79, this is 0.79. Is there any difference in the density? No. And then it would have been impossible to tell. And so if you only had two sig figs of precision, no way could you tell the difference in the density, right? There's no way you could tell if that's pure methanol, pure ethanol, or mix of ethanol and methanol. Right? Does everybody get that? And so people pay a lot of money. People pay a lot of money for high precision instruments. In fact, I need to post our current price list for lab equipment. You'll notice the volumetric glassware is kind of expensive. You know, you break one, that's $100 out of your pocket. So you got to be careful with some of it. If you break multiple items, then you could be out a couple of $100. Well, a couple of $100, that's not so bad, because I think when I finished organic chemistry, my bill was over $200 breakage. So this method works better if these are more dramatically different and we get a lot more digits here, correct? And so to answer this question here, how precisely could you determine the composition of an ethanol-methanol solution? By measuring its density with a pictometer? How precisely? To 2 sig figs. That's how precise you can be. Okay, now let's go ahead and calculate, because usually we don't answer questions like that. The normal question we answer is one where we're trying to solve for something specifically. And so let's go ahead and solve for that specifically. You know, if we carried more digits here, we could be more precise, but this isn't exactly fair to carry these digits because of the pictometer. You know, there's still uncertainty there. All right, and so what was our density of the mixture? Okay, let's go ahead and, the density of the mixture that I gave you was 0.7905 grams per milliliter. This is equal to 0.000020 grams per milliliter per percent methanol. And then we have percent methanol plus 0.7894 grams per milliliter. We're solving for percent methanol. If we solve for percent methanol, then we're going to subtract that from both sides. Actually, we might not even have as many sig figs when we do the specific example here. Let's see. And so subtracting this from both sides, we get 0.7905 minus 0.7894. Can't read. 7894 grams per milliliter. So 5 from 4 is 1, 10 is 1, 0, 0, 0. Okay, we're still at 2 sig figs. We might have even gotten less. We could have had less than 2 sig figs. How could we have had less than 2 sig figs? Is it possible to have less than 2 sig figs? Yeah. Do you see it? This is what I mean by, a lot of people just focus on one tree, but if you look at the range, what are the ranges of the density of the mixture? What is the range of the density of the mixture? We just looked at that, but let's say, you know, where did this number come from again? I gave it to you. But what if I gave you this number? What if I said the density of the mixture is 0.79? Oops, what am I doing? Not 79. Let's say, what if I said the density of the mixture is 0.7900? If I gave you 0.7900 as the density of the mixture, right? Then what would the subtraction have yielded? And so let's do this as an aside over here. An aside. If it were 0.7900, and then I subtract 0.7894 from this, what's my answer? How many sig figs is that? 1 sig fig. And so the precision of this varies from 1 sig fig to 2 sig figs. Is that very good precision? No. And so we can kind of think more of the range, because the range of values, I could pick anything from 0.7894 all the way to 79, I think it was 14, right? The density can take that entire range. In fact, you know, we don't have to do this. This is solving it using this equation, right? But we could have easily solved it using just basic graphing technique. Basic graphing technique is like this. You know, this is 0 to 100%, and then we have a line like this. And so all we do is we go to 7905, and so at the top here, this was 7914. At the bottom here, this was 0.7894. And so we just go to 0.7905, and then draw, if you want to graph this. You know, most people don't want to graph this, because a lot of people hate graphing, right? Because you got to break out the graph paper and then, you know, draw the points, label the axis. It's a lot of work, right? And so rather than graphing this and getting a straight edge and then just going out here, oh, it's got to be around, what, 90%? Something like that? Methanol? Rather than doing this, I said, okay, let's get the equation of the line and then let's go ahead and solve it for y. And so we're solving this for y, and then get that. And so what we have now is we have that, or solve it for x, sorry, quadruple 020 grams per milliliter per percent methanol times the percent methanol that we're trying to get is equal to 0.0011 grams per milliliter. Okay, now we divide both sides by this, and so that we get the percent methanol is equal to 0.0011 grams per milliliter divided by 0.000020 grams per milliliter per percent methanol. This is under the sign here. So grams per milliliter cancels out. We invert this and flip it up, and so we get percent methanol. So can somebody calculate this? 55? Oh, wow. My graph here was way off. It's more like 55. So this is more in the center. So 55 point what? Okay, 55.0. So we'll carry that extra 0. So 55.0% methanol. It's a two-component mixture. And so here we use another equation. If it's 55% methanol, what is the percent ethanol? It's got to be 45% ethanol. There's only two things in this mixture, and they have to add up to 100%.
How did you invert the percent?
Oh, because it's in the denominator here. And so just when you're dividing by a fraction, you invert the fraction and multiply. So now the percent methanol is up here in the numerator. Okay, there's this little fraction. The milliliters and the percent ethanol are on the same line. That's why.
You said something like,
Oh, just the units. I'm talking about the units. Invert the units and multiply, not the number. What do you think about the graphical method? I think the graphical method is pretty straightforward compared to the system of equations method. Let's do the system of equations method to solve this. I don't care which method you use, because I've had people saying the graphical method is too confusing. I'd rather you solve these multiple unknown problems using system of equation. It's fine with me. You know, I don't care which way you solve these types of problems. All right. Okay, that method was the graphical versus system of equations. So let's look at the system of equations next. And so we have two unknowns. You just call, x, we'll call it as percent what? Maybe x we'll call percent methanol. Y we'll call percent ethanol. Okay, give me two equations. Well, actually, give me just one equation. Let's start with one equation.
X plus Y equals 100.
Yeah, good. And so one equation will be x plus y equals 100%. All right, give me another equation.
Point 7894 y plus 0.79.
7894 y plus
0.7914 x equals 0.7905.
Okay, grams per milliliter. Okay, so let's put in some units here. Make sure the units work out. Unless, do you want to modify this a little bit? This is grams per milliliter. What are the units for y? Percent. And so we get grams per milliliter times percent, so fix it. Very close. The simple fix, just fix it.
Move the decimal.
Okay, we can convert the percent into a decimal, but how would you show it here in an algebraic equation? You wouldn't write move the decimal 2 over, right? You would do something mathematically. Tell me what mathematical function you would use to do it.
Over 100.
Over 100, good. Yeah, so y over 100, x over 100. There we have it. And so that would be, that's perfect. These are the two equations you can use and then solve them, right? Okay, this is why I call this the tree method, because when you solve this, you're only solving it for this composition of mixture. Do you see the range? Well, I guess you could see the range just mentally, but graphically like this. And so by using a graphical method like this, then we can just see, as the density is going to range from here, the percent composition is going to range from here to here. And so we see the entire range here. With this, we're just focused on this composition. And that's all we're going to solve for. And so other compositions, a lot of people can do this in their head. They just look at it and they do it. Because you know what this looks like? Do you guys remember solving for the average isotopic mass? Do you guys do that? The average atomic mass, we call it. Do you remember doing that? That's what we're going to do in this chapter, chapter 2 today. All right, so solve this. Other than that, too bad. And so, like I said, a lot of people don't mind. They like to solve this, no problem. Go ahead. Or you could use the graphical method, whichever is more comfortable. Okay, we're going to see these multiple unknown problems in a bunch of the chapters, actually. And actually, we're going to learn one more technique for solving this as well, because in one of the chapters, the multiple unknown problem is actually has a twist in it that makes it a lot more difficult to solve. It's not going to come until chapter 6. But for right now, this is just your standard multiple unknown type problem. All right, those are kind of some of the techniques that you'll need. You know, a lot of these other problems are similar. You know, sometimes you'll use system equation. Oh, it just jumped again. Next page. Sometimes not. And so we'll just take a brief look. I was going to cover all these, but I'm not because I'm running out of time. But if we look, you know, the following equation can be used to relate the density of liquid water. You know, have you ever looked at the density of water in a graph? Can you visualize what happens to water with temperature? Usually, in Chem 4, you've worked with this table. You know, the table is the temperature versus the density of water. You've got a whole bunch of numbers here, right? But to get a better visual picture of what's happening, we need to graph this. When we graph this, we'll see the density of water actually decreases to about 4 degrees C and then increases. It hovers around 1, so these changes are very small. If we fit this equation, you know, what kind? Is this a linear? No, this is non-linear function, right? It's a curve. Non-linear functions, the equations are going to be more difficult. And so when we map out this equation here, this is the function that fits it. You know? And so where did this equation come from for the density of water? Somebody tell me, did this come from theory? Observations. This is an empirical equation from observations. Somebody just plotted it out and figured out what is the mathematical function that fits this weird curve. This is it. And so the following equation, and you know what? This equation is good only in the 0 to 20 degrees C range. What happens beyond 20 degrees C? Maybe what happens is this equation goes like this, but the data go like this and start to deviate. And so it's only a good match down here where they get a decent R squared value up to 20 degrees, and then beyond 20 degrees they need some other mathematical function to figure it out. You know, and so that's the thing about, you know, this is not from theory. In theory, you just want one function that describes the whole thing, right? That you would like to get from theory. We don't want to mix and match and this kind of stuff. But the thing is, these are very useful. The reason these are very useful is rather than plotting it out and then figuring out what the density is at different temperatures, we can just go ahead and calculate it. Or rather than doing interpolation, you know, have you done interpolation? Let's say the data goes from 24 degrees C and then jumps to 25 degrees C. Well, what if you're at 24.1 degrees C? What should you do? Should you use the value of 24? No. What if you're at 24.2, 24.3? We don't have any data there. What do you do? I want the density of water at 24.3 degrees. Unfortunately, I only have 24.0 and 25.0. I have numbers for 24.0, 25.0, but no numbers for 24.3. What do you do? Have you done interpolation? Yeah. I guess they don't cover interpolation much in algebra. I did tons of interpolation when I was taking algebra. You know why? Because when I was taking algebra, we had to use a lot of tables of logarithms. even though calculators were available that could do the logs, we had to do them manually by looking in the table of logarithms and then interpolating. We did something called linear interpolation. This is what you're going to do next week in Experiment A. And in Chem 4, I have all my students do linear interpolation because in Chem 4, there's a table of densities, and they have to interpolate between two density values to get it. But anyway, if we want 24.3, what we do is we assume that the increase between 24 and 25 is linear. Is that a safe assumption? Well, it depends on how tight the data is. You know, the closer the data points are to each other, then it's a good assumption. But if the data points are dramatically different, then things can deviate from linear. And so the closer they are together, the better. And so linear interpolation is, you know, if we have this, then what is this? Well, we just did it over there. You know, the same kind of concept. You know, if it was 24.5, it's easy. You know, if it's 24.5, then what is the density? Assuming it's linear. In the middle, right? We just did it. Well, there's nothing new. But anyway, here, it's nice to have an equation like this because we can determine the density. In fact, the 4 sig figs determine the density of water at 10 degrees C. Well, 10 degrees C, that's only 2 sig figs, or 1 sig fig. How do we get it? How we get it is we just say that at exactly 10 degrees C. What is approximate density of water? At what temperature does water have a density of 0.9986 grams per cubic centimeter? At what temperature? Okay, so here we plug in the density over here and then we solve for T, but when you look at T, we have a T squared term here, T to the first term, and T to the 0th term. What type of equation is this? Quadratic. And so, you know, this is, in 83B, we actually have to use the quadratic formula from algebra in order to solve this. And then we have to get this into quadratic form, which is a pain, but doable, right? So that's it. In the following way, show that the density passes through a maximum somewhere in the temperature range. Oh, a maximum. You know what? I have this inverted. Sorry. The density hits a max at 4 and then decreases with temperature. Somewhere in the temperature range in which the equation applies by estimation, by graphical method, you know, or by different. If you've taken calculus, actually, has anybody taken calculus? You take calculus, then you can just figure out the max of this function. It's probably the easiest. But here we just do graphical methods, just plot it, you know, get some points, plot it. Estimation is just guesstimate, you know, guess and check. All right, so if you look at some of these other problems, then you can get a good feel for what we're doing. But I don't have enough time to look at all the problems, so we're just going to move on. Oh, actually, there was one more thing I need to talk about. What did we assume with the this problem over here, methanol and ethanol? That's linear. You know, as the percent methanol increases, the density changes linearly, right? Is that a safe assumption? Well, that's an assumption we make often. But take a look at number 85. A tabulation of data lists the following equation for calculating densities of a solutions of naphthalene, which is an organic chemical, and benzene. And so we have a two-component mixture here, naphthalene and benzene at 30 degrees C as a function of mass percent of naphthalene. If we look at it as a function of mass percent of naphthalene, take a look at what happens. Is it a linear function? How can you tell? Well, the squared term, percent naphthalene squared. It tells you it's going to be a funky curve-like function. not so simple. Okay. And so in this way, for a mixture of naphthalene and benzene, this is a different type of percent though, because you know, what types of percentages do you deal with in chem, or have you dealt with? What types of percentages? Percent by mass, percent by, did I talk about this yesterday? Percent by volume, pressure, mole. Mole, molecule, or atom percent. What type of percent is this? I didn't specify. Is this a mass percent? No, this is a mole percent. And so mole percent should behave like this. This is a different kind of percentage. This is a mass percent. Although, actually it should behave similarly. But the density of pure naphthalene, etc. Anyway, so this one's a little bit more complicated. And that often happens because oftentimes we'll just look at a small section and say, okay, it's linear in this temperature range. But beyond that, maybe it's not. And try to fit that certain part of it with some empirical equation. Empirical equations are quite common in chemistry, and this is just another empirical equation. All right, and so one of the things that I was going to do, because if, you know, since, let's see if I can get the page to change here. What time do we go to? 10:55. 5 more minutes. Well, while we wait for this to load, if it's going to load or not. Okay, if it's not going to load. Am I going to throw out a nonlinear? You think I'm going to throw out a nonlinear multiple equation, multiple unknown? Have you solved that? Well, most likely not. No. Not unless I simplify it quite a bit. But so you can assume that most of these multiple equation type problems that you're going to get are going to be linear functions. All right, what I was going to show you there are, you know, if you need some refresher and review, there's a whole series of review questions in that chapter, and those are really good to test your knowledge quickly, to see where you stand. But we're going to move on to chapter 2, since chapter 1 is mostly review. And chapter 2 is also mostly review. Chapter 2 deals with atoms. Okay, so the question I always ask is, do you believe in atoms? Let's say your friend goes, you know, do you believe in atoms? What would you say? Yeah, right. And then your friend asks you to prove it. Prove to me that atoms exist. And then what would you say? Do you believe in atoms? Prove it. We take a lot of things as like postulates. You know what postulates are? Taken without proof, right? And so, do you believe in atoms? Yes. Well, prove it. And then what would you tell your friend? Read the textbook? There's plenty of proof in the textbook. You know, I don't. This is what happens. This is why, you know, the types of questions you get. You know, they talk about this. You know, it's the type of question you get. It's the type of question you get accustomed to. Once you get used to that type of question, then those are the only types of questions you're accustomed to, right? And so there's this whole big thing about math, you know, what types of questions do they ask in math, and, you know, what different types of questions do they ask in different countries about math, because they ask different types of questions, ask things differently. Well, one of the things that happens is you get subject to oral examinations. Like if you go to graduate school, you have oral examinations. What type of questions do oral examination people ask? Or you go to a seminar, and let's say you have to present a talk at a seminar. What types of questions do people ask? Well, the types of questions that people ask are kind of different than the types of questions you answer at the homework. The homework problems are very specific. Target, you're given all the variables. Questions at seminars and oral examinations aren't. They're very broad. They want you to explain the whole picture, right? Not just one specific problem. And so let's say if somebody asks you, what proof do you have that atoms exist, can you give it to them, right? And so let's see, do we have time? We have 3 minutes left. Why don't you, we'll just do another practice quiz. Why don't you work with your partners and come up with some kind of proof that atoms exist in the last 3 minutes? Since I'm not going to take roll again, and another class is going to come in here, I need to see who the late attendees were. The late attendees, just circle your name so that I know you're here. You were here at least late. But go ahead and write down at least one piece of proof. Can you come up with just one piece of proof that atoms exist?